Okay, so this is session 9. The reading for this session was chapter 2, section 5, I believe. Let me check the book. It was on, so chapter 2, abstract structures. Yeah, section 4, products. So let me just share my screen. Share screen. Okay. Everybody should be able to see my book now. Okay, great. So my notes on this are here on the screen. So I guess I'll just go over those to get us started. Okay, so Awodey says that products are, he says, probably the first example of category theory being used to define a fundamental mathematical notion. So so products are, a fundamental mathematical notion that comes up in all kinds of mathematics. And it's the earliest example of being able to define such a notion purely in terms of category theory. And this definition in category theory is given in terms of a universal property, or a UMP, a universal mapping property, as he calls it. So he gives the example of the Cartesian product of types, which we're just going to use that to sort of orientate ourselves to products. So we're all familiar with the Cartesian product of types, or what he calls, he says, sets. Excuse me. So, yeah, the product type of the two types A and B is just the familiar pair product type, A comma B in Haskell. So there are two projections out of this type. There's one arrow from A and B to A, and there's another arrow from A and B to B. Right? So we can get the B out when we get the A out, and these in Haskell are called first and second. And indeed, this follows this sort of law that A comma B, or any C of type A comma B, is the same as first of C comma second of C. Seems obvious. If we deconstruct the product and construct it again, that's the identity. The diagram in the middle of page 39 captures this notion precisely. 39. Yeah, so here in the middle of 39. So we have an A, which is an arrow from unit to A. So if we can construct an A and we can construct a B, then there's some unique way in which we can construct an A comma B, right? And that's just the comma operator. So it takes our A and it takes our B in such a way that makes this commute. That is, this line 21 law here holds. Okay, so we have an A and a B and a first and a second, and we have an object A comma B. All right. So a more abstract definition of product. So this is just using sort of unit as our index, or as sort of the orientation. So this is how we can construct products out of nothing other than the elements of the product. But then a more abstract way of defining this is if we consider generalized elements. So instead of considering unit here, we consider some other type X, right? So given an object P, which is going to be our product, and then arrows P1 and P2 that go into the components of the product, A and B, that object P is a product if for any other object X that has these arrows also into A and B, that is, it's sort of a diagram of the same shape with the same sort of endpoints on it, then there is a unique map from X to P that makes that diagram at the bottom of page 39 commute. That is going from X to A via this map X1, and going from X to B via this map X2 should be the same as going through U and then through the map P1 and P2. So in the category of types, we can imagine that this P is the pair, A comma B, and then this X is some other type that we can extract both an A and a B out of. We can extract an A, we can extract the B, and we can also extract the product, A comma B. Then if that's the case, that is, if we can extract an A out of it, we can extract a B out of it, then we can also go through the product. That is, we can sort of factor out this arrow x1 and x2 into something that extracts the pair and then extracts, the left half of the pair or the right half of the pair. Does that make sense to everybody? All right, so we can imagine that this is like string comma int, and this is like person with like a name and an age or something, or a name and an age and an address, right? So then there are many different ways that we can get a string and an int out of that. But for each of those, for each of those ways that we can get a string and an int, we can also get the product of the string and an int, and then go from there to, to either the string or the int. Right. So this is a sort of a universal property. So it's saying that this P is sort of the product. Okay. Right. So he says that. Okay. Yeah. So the map U that's sort of in the middle of the diagram factorizes x1 and x2. These hypotenuses here. So the map U factorizes these two into P1 and U and P2 and U respectively. So U is sort of their common factor. And then P1 and P2 are unique in that they don't factorize further, so they are in a sense prime. In fact, what we have here is sort of, I'm going to see if I can do a little drawing here. Okay, so we have some object A, right? And we have some object B over here. I'm gonna just draw arrows here. And in the middle, there's some object X that we can project an A out of and a B out of as well. And then we have some other object Y that can also do this, etc. Right? In fact, what we have is actually a whole category of diagrams like this. A whole category of diagrams with endpoints A and B. So A and B are the objects that we're going to take the product of. And there's a whole category of these diagrams. And an arrow in that diagram is just going to be an arrow between, an arrow in that category is going to be an arrow from X to Y. So I'm just going to put like here. So there's an arrow from X to Y, there's an arrow from X to Z, an arrow from Z to P, and then composite arrows, in the usual sense, right? So
should these be like commutative diagrams? Like an arrow between these objects in the category?
Yeah. Well, I'm not sure what you mean exactly.
Like, I think you'd need like a if you go from like X to Y to A, that's the same as going from X to A, right?
Yeah. So these are all the same A, right?
Right, but like, I think you need to further say that there's an identity morphism when you change that.
Oh, an identity morphism on A?
Yeah, like, so you got this category of like cones from X to A to B, right? Or X and A to B?
Yeah, so I just have a category of things that look like this thing on line 154.
Right.
And then there's obviously an arrow from A to A. Yeah. There's obviously an arrow from B to B. And then in order to construct an arrow between 154 and 157, so I just need to say that, well, that diagram now commutes by inserting this arrow from X to Y, right?
And you're saying the whole thing commutes?
Now I'm saying the whole thing commutes.
Okay, cool. I guess that was the part I missed.
Because these two A's are the same. Like the situation is actually that this arrow from Y actually goes into this A right here. right?
Maybe continue, and I'll bring it up later if I'm still concerned.
Okay.
Yeah.
So anyway, what I'm saying is that the situation is basically that we have all these objects that are sort of like candidate products, right? X, Y, and Z, or whatever, because we can project an A and a B out of them. And what we actually have is a whole category of them. And then at some point, there's going to be a terminal object in that category that does not factor any further, but which has a unique arrow, a unique homomorphism from every other object in this category to it. So P then is going to be at the sort of the bottom of this category, such that for every other object that looks like this, there's going to be a unique arrow from that object to P. Does that make sense? And in our category of sets, this is going to be the type A, comma B. Does everybody follow that? So this might be like A, comma B, comma C, and this might be like person or something. I don't know. So a bunch of other types that we can get an A and a B out of. But at the bottom of that hierarchy is going to be sort of a universal or canonical product that all of the other kinds of things that we can project into A and B are also going to be able to project into it in a unique way. And that's kind of cool.
When you project from like that bottom type, A, comma B, back to say the triple, can't you pick any C? So why does that, how is the arrow back from A to B from a tuple to a triple?
There is not necessarily an arrow that goes back. Like you can't go from A and B to A, B, and C without a C, right?
Doesn't it say that these things...
But you can do
up to isomorphism.
And so it wouldn't be a terminal object.
Sorry, what?
You can pick an arbitrary C and you can go backwards, but it's not a unique morphism, so that doesn't change the terminalness.
Right. So what I'm saying is that this diagram at the bottom here is the terminal object in the category of such diagrams. And that's what makes this the product.
Interesting.
Yeah. I can go over like, I made a bunch of notes about the product as a universal construction, and we can go over that sort of at the end. It's a little bit, it took me a while to figure that out this weekend. Okay. So now we have our definition of a product, right? So it's any, P, which is at the sort of the bottom of such a hierarchy. Okay, so he makes a remark that says, as with any other universal mapping properties, or we can just say universal properties, it has two parts. There is an existence part, and that existence part in this case says that there exists some mapping U that makes that diagram commute. The diagram at the bottom here on page 39. So there exists some U here in the middle for every X. And then there is a uniqueness which says that for any two arrows V and U that both make the diagram commute like that, they are in fact the same arrow. Right? So there's only one such arrow that makes the diagram commute. For any given X, there exists one, and it is a unique one. Right? Uniquely determined by X, A, and B. Okay, so then he goes on to say that products are unique up to isomorphism, and he shows that in the middle of page 40. So, he says, okay, suppose that there are two different products, P and Q, and they're both products of A and B, right? We can show that they're the same. And it's pretty easy to show using just the diagram like this. So suppose that P and Q are both products. So because of the existence condition, there must exist an I, right, which goes from P to Q. There must exist a J that goes from Q to P. Because if P is really a product, then for any other Q, right, there exists a U that makes that diagram commute, right? And same reasoning for P to Q, right? So I and J definitely exist. We know that. And we know that I and J are also unique, right? There's only one I that goes from P to Q, and one that goes from Q to P. And what does he also say? Yeah, so it follows from that uniqueness condition that J compose I is necessarily the identity, because so we can follow this, that so if we go I and J and then P1, this diagram says that should be the same as just P1, right? So if that's the case, then I and J are the identity, because P1 compose, if I and J compose P1, right, going down the diagram and then up and to the left, if that's the same as, if IJ P1 is the same as P1, then IJ is necessarily the identity, right? Because identity and P1 is also P1, right? So going down and up is the same as just going down from P to A, right? So I and J are necessarily identity, so they're inverses of each other. Therefore, P is Q. Okay. So it's not that P necessarily is Q, but it is isomorphic to it. In fact, there is more than one there can be lots of different products in a category, but what this is saying is that they are all isomorphic to one another. Okay, so why is it important that products are unique up to unique isomorphism? And I gave just sort of my remarks on that. My remark on that is that it gives us the ability to talk about the product of two objects. So the major reason that this is important is that, for instance, if we take the product of two types, A and B, and then we take the product of two different types, C and D, that product is also different, right? So I was just saying that if A and B is isomorphic to C and D, then A is necessarily isomorphic to C, and B is necessarily isomorphic to D. And so that allows us to sort of reason compositionally or sort of homomorphically through products, right? So if we can reason about the elements of the products, then we can also reason about the products. He also talks about how an arrow into a product is the same as a pair of arrows. So an arrow from X to A and B is the same or isomorphic to a pair of arrows, one from X to A and one from X to B. And the proof we can give in Haskell. So going from a single function to two functions is just, we take first compose F and second compose F and put those in a pair. And to unpair, we just apply, we take the two functions F and G and we apply them both to the same argument, X. Make sense? So what we can say about this is that arrows distribute over products in their codomain. So this arrow here has a product in its codomain. And we can say that the arrow actually distributes over the product. So what we have then is a product of arrows with the elements of the product in their codomains. So these, so the two diagonals of the product diagram, or the sides here, x1 and x2, or p1 and p2, right? They uniquely determine the central vertical arrow, u. And this is the same idea that, for instance, a times b to the power of x is the same as a to the power of x times b to the power of x. So exponents distribute over products. And that is not a coincidence. Yeah, so also in logic, we can say if x implies a and b, then x implies a and x implies b. Right? he also mentioned that arrows from products. So if we have an arrow that takes an A and a B and produces some Y, that isn't reducible to anything more fundamental. So one of the wins that we get from taking products in a category is that it allows us to compose with arrows like this. So it allows us to have a notion of arrows that take two arguments and to compose with them, because we can construct products, and then now we can compose with arrows like this. So yeah, arrows do not distribute over products in their domain, just like products don't distribute over exponents. But he says they curry and uncurry, and that's sort of a digression that he gives. So if we have a function from a product to some type C, that's the same as having a function that takes an A and then returns a function that takes the second argument and returns the C, right? So that's his curry. And then we can uncurry. So if we have a function that takes one argument and returns a function that takes the second argument and returns a C, that's the same as having a single function that takes a pair, and that's uncurry. And that's the same idea, again, that a to the power of b all to the power of c is a to the power of c times b. So that's just looking at the same fact in a different category. And also, if we look at it, in a Boolean algebra as our category, then we can see that it's the same as saying, well, if A implies that B implies C, then both, if we take A and B, that implies C. Yeah, further little digression is that products are unique up to isomorphism, but they are not unique up to identity. So the products, there's not just one product in a category necessarily, but if there are multiple products, they're all isomorphic. So here I give a different product so it's not the pair A and B, it's a function. So this function is a higher order function, which takes a function that receives an A and a B, and it produces an R. So, sort of obviously, if you can call a function with both an A and a B, then you necessarily have an A and a B, right? So this is saying, like, if you can, give me a process that takes an apple and a banana and gives me a rodent, I can give you a rodent, right? Couldn't think of a fruit that starts with R. All right, so so two products here, so I take a pair and I turn it into my product type. That's just, apply the function f that is given as this argument, apply it to both A and B in the pair. And then I can turn my product into a pair just by sending it the comma function that produces the pair.
Can I pause you for a second?
Yes.
I am wondering whether or not products exist in all categories. And I think the answer is no, but I don't have it necessarily a proof.
Right. The answer to that is, in fact, no.
Okay. So I think, like, a particular monoid is a category that does not have a product.
Does a monoid not have a product? I'm not certain about. I want to say the answer to that is no, but I haven't worked it out.
You have an example of one that doesn't have a product?
I don't. I don't have one ready. But that's an exercise that we can work out, and I'm sure actually that Awodey will give us one later on.
Yeah. Cool. I'm curious about this.
And he actually, in the following section, he gives us a number of examples of products. Right, so we'll go over that next time. Products of structured sets, and then products of topological spaces, and
that's kind of the opposite of what I want, though, right? Is a category which doesn't have products.
Yeah. So 2.6 talks about category products.
Although he talked about that, he doesn't point out probably.
Does he not talk about categories that don't have products?
I don't see any. but that's okay. I'll dig into it.
Yeah, I'm sure we could think of one. I mean, can we think of like a really simple one? Like, does the empty category have products?
It kind of does trivially, right? Like vacuously.
Yeah. Does the category 1 have products? Yeah, I guess
I
it
think so
does.
because it's identity, right? It's itself.
Vacuously, yeah. Okay.
Yeah. Anyway,
What about the category 2?
I think so.
We have two objects and there's an arrow between them. Yeah. Then we can take no, wait. Can we take a product of either of those objects with either one of the other ones?
If you have like category 2 and you got A goes to B, then your B is kind of like your A and B in the generalized sense.
Mm-hmm.
And your A is the X. And so that projects to both of those things. And your product is still 2, or still the second part, with identity as all of your morphisms, as all your projections.
Okay, so the second object is then always the product.
Yeah.
And the only element is the okay.
I ran through like a bunch of these and I didn't find anything that didn't have a product. So that's
all right.
But that's okay.
We can probably
figure it out later.
Yeah. I'm sure there's like a canonical example that somebody watching this video is now screaming at us. Okay, so that's products, and it's an example of like a fully abstract category theoretic construction, where like we don't need anything other than category theory to talk about. And I wanted to figure out if I could construct the products from the universal construction. So we've been very sort of hand wavy about like what does a universal mapping property mean, right? But if we go to Wikipedia, let's go to Wikipedia. Here we go. Oh, that's not what I wanted. Yeah. Okay. And we search for universal property. So there's a formal definition of a universal property here, which is super helpful. So that's saying that, if we have a functor from a category, one category to another, and then we have an object in the second category, in the target category, then there is a whole category of morphisms from X to U, from that object to an initial object in this category, which is the comma category of X down to U. And it says, in other words, it consists of a pair, A and phi, where A is an object of the source category, and phi is some mapping that goes from X to U of A, right? So it's some pair A and phi that makes this diagram commute, right? Whenever Y is an object of D, F is this kind of morphism, and there's a unique morphism from G, from A to Y, that makes this diagram commute. Anyway, this is all like super abstract, but it tells us very precisely what a universal construction is. So I wanted to see if I could actually come up with products from that definition. Okay, so a universal property is either an initial property or a terminal property, right? So those two things, we abstract, or there's a common concept that is the universal property, and it's splits into two halves, and there are universal properties that are initial, and there are universal properties that are terminal. What they are initial and terminal objects in a category like this. Okay, so what I took was basically just this Wikipedia definition, and it said, so okay, a terminal morphism from this functor u to this object x of c. So there's like a whole category of morphisms from u to x, and the terminal such morphism is it's the terminal object in this comma category of morphisms like that, right? We call that category u down to x. It's a category. What the objects of the category are morphisms from u to x, where u is a functor from some category D to some other category C, and x is an object of the category C. Okay. So
Sorry, just to clarify, that's like the image of something under this functor projects down to x.
Yeah.
I'm a u of x.
It's u. No, it's not u of x.
It's like so like u, right? And then for any morphism you can find that projects down to x after that functor.
Let me see. So in here, yes. So if you can go from u of y down to x, and u of a to x, right? So one of these.
We're restricting like the category D to only the objects in that who project to object X, right? In our functor?
Yeah, it's very similar to like the slice category, right?
Yeah.
So it's like the slice category where we have like all of our arrows go into one object X, right? And then we have like objects of the category like A, B, C, or whatever, and then we have an arrow in that category that just like maps, Y to A or whatever. But here we have a further structure, which is that this this category is a category of morphisms like this, like from U of some object down to X, where this Y is an object in a different category, right?
Yeah.
Right.
So trivially, I guess, if U is the identity functor, then the only things in U comma X would be X, right? Or like morphisms on X.
Yeah. So
I'm just trying to wrap my mind around this U construction. Or
so if U is the identity functor, then this is just this nice category over X.
Okay, cool. That's what I. Great.
But we can sort of generalize that notion and say like, oh, what if we have some other functor, right? And then we have this thing which is called comma category, which involves some other sort of source or sort of index category.
Yeah.
And so what we have here then is a whole category of morphisms that have this shape that go from U of Y for some object Y in a different category down to X. X is fixed, so all of them go to X. There are morphisms then from X from U of Y to U of Z or whatever if there is an arrow in the source category from Y to Z. And then what we're saying is that there's some terminal object in this category that has a unique morphism from all such other arrows, right? Yeah. So this phi here is then sort of at the bottom of that hierarchy, right? And you can sort of now see that this is similar to the notion of a product, right? But we had a whole category of diagrams that all looked very similar. So here, the diagrams that all look very similar have the shape of F. So there's a whole category of things that have the shape of F, and there's one which is at the bottom of them all, and that's the terminal arrow in that category. So it's a terminal object in the common category of morphisms from U to X. So each such morphism consists of a pair, A, where A is an object of D. So back to here, that's that A, and a morphism phi, which is that one here. Am I saying that right? Phi? I think so. And that one goes from U of A to X, right? So, and that's a morphism in our category C. And that has to make that diagram that we just looked at commute, which means that this, what's called a terminal property, which is more generally a universal property, it makes this, it makes that diagram commute because this property is satisfied. says that for every other object in D, y, and every f from u of y to our object x, there is a unique morphism from y to a in D that makes that diagram commute such that going f is the same as going phi and then u of g. That is, phi is a common factor of u of g and f, right? No, sorry. It's just a factor. Right? It's just a factor, and phi is going to be prime in the sense that it doesn't factorize further. Okay, and then so an initial morphism then is the other way around, where we have, we basically reverse all the arrows. Where we have the same kind of structure except all the arrows go the other way, and our sort of universal morphism is at the top, where all the arrows go out of it rather than into it. Okay. Okay, so the product that we looked at can actually be seen as a specialization of this situation that we're looking at here, this universal construction. And so how do we do that? Well, let's look at the product as a terminal morphism. So take a category J, and we're going to say that this category is a discrete category with only two objects. Then if you recall from chapter 1, a discrete category has only identity morphisms. So it has no morphisms between the objects, only identity morphisms. And so this thing has two objects. Each one of those objects has an identity morphism, and there are no other objects or morphisms in this category, J. Okay? Then each functor from J to some other category C will pick two objects from C, right? That's kind of obvious, right? So we have two objects in J, and so if we have a functor from J to C, it's going to pick some two objects from C. So then there's a whole category of such functors. And that whole category we're going to call C to the J. And so it's a category of functors from the two object category, discrete one, to the category C, and natural transformations between those functors. And what we've just constructed is the product category C with C. Right? The product category C with C, right? It has as objects pairs of objects from the category C, and it has as arrows pairs of functions from the category C. Right? So if we have an object in C paired with another object in C, then we can compose the arrows if we just have like a pair of arrows that, one of them goes from the left one and the other one goes from the right one, right? So we've seen product categories in chapter 1. Okay, so this thing then goes on to say that there is a functor, which we're going to call delta, that goes from our category C. And it's nice to orient ourselves and think of C as being Hask. So then it goes from our category C or Hask to the product category. So C to the J, or equivalently, it goes from C to the product category of C with C, right? So it maps each object C in C to the constant functor, which has type J to C. And that constant functor maps both objects in J to the object C. That is, delta of C, where C is some object in the category C, is the pair, or the sort of the magically constructed two objects C and C, right? So delta of C is just the pair C and C. And then delta of F on morphisms is just the pair F and F, okay? So now we have this cool functor, delta, that goes from the category C to the product category of C with itself. And all it does is just like duplicate the objects and duplicate the arrows. Great. It goes on. A product in C of A and B, two objects in C, is then a terminal morphism from that functor, delta, to the objects A and B in the product category C and C, right? So it's going to consist of some object P in C, which is going to be our product, right? and then a morphism from P and P to A and B in the product category C and C. So what I'm doing here is just filling in the definition of the universal morphism, or the terminal morphism here on line 117. So all I'm doing is just like substituting equals for equals here, and I get that it's going to be some object. It's going to be a pair, like A and Phi, where our A is then the product P, and there's going to be a morphism from the pair of P with itself, so in the product category, to A and B, also in the product category. Right? And you'll note that that is really a pair of morphisms in C, right, by the definition of the product category. So it's a morphism from P to A and a morphism from P to B, and that's going to be our first and second morphisms. Yeah? So that satisfies this terminal property, since for every other object in C, x, and then we have some function f that goes from x and x, so delta of x, to our A and B, there's going to be a unique morphism from x to P. So from x to our product. That makes this whole diagram commute. I called this phi here, and I actually wanted to call it, did I call it phi? Yeah. Sorry. I forgot to give it a name here. There. So f should be delta, is a phi of delta of g. So if we expand that out to the category Hask, then the product of the types A and B is the type P, and there are two functions, first and second, from P to A and from P to B, such that for every other type X, and any function f from X to A, and G from X to B, there must exist a unique function H from X to P that satisfies this equation. So, f of x paired with g of x is the same as first of h of x paired with second of h of x for all x of type x. So the long and the short of it is that what this universal property is really saying is that these two things are the same. The functions into pairs are the same as pairs of functions. So yeah, if you construct that from the universal property.
Is that true in general?
Is what true in general?
That x goes to A to B is the same as x to A to x to B? I feel like that is not true in general.
It is in general. It is true for all categories that have products.
And exponents, right?
Just arrows, right? If you have an arrow into a product in your category, so if your category has products and you have an arrow into a product, that's the same as having two or a product of arrows.
But you can't represent that product of arrows unless you have like internal exponents, right?
You can't?
I don't think so.
Well,
it's a different category otherwise, right?
Well, I think you like I say, you can always take the product category using this construction here at the top. Yeah.
Right, but the product category is different than the category. I guess.
Yes, but I'm saying that if this mapping exists, then you can go and you have this functor delta, right? And that functor delta will allow you to take pairs of arrows like this. Right?
Yes.
And what I'm saying is that if this construction exists, then this is true. Make sense? Then line 144 is true if everything that precedes it is also true in your category.
Maybe I'll bring it up with you after.
Okay.
But I guess we're done anyway.
Yeah,
but,
I guess we only have 4 minutes.
I think there's like a type error here, unless I'm really mistaken.
Okay.
in the sense of like X goes to A to B. That's in category C, but the product of X to A and X to B, that's in category C cross C. And so those are different categories.
Right. Yes. No, I see what you mean. This actually is, yeah. So I guess it's a good point. Like, is this pair A and B, is that the product in C, or is that the object A comma B in the product category C with C? Right.
I think it has to be the first one because the object X doesn't exist in C cross C.
Oh yeah, that's true. That is true. Yes. So then you have to have, yeah. Okay, I see what you're getting at. So this has to be in C. Like this has to be a morphism in C, and this has to be a pair of morphisms in C. So this is actually an object in C cross C, right?
Right.
Yeah, I see what you mean.
Okay.
But I think what everything above here is saying is that you can go from this object in C to this object in C cross C. And
Okay.
vice versa.
Let me think about it. I'm not convinced one way or the other.
Right.
Cool. Can you post these notes, please?
Yes. Yeah. Sorry, I haven't been posting the notes, so I'll definitely do that.
Thank you.
So,
Cheers.
anybody else have any concerns, questions, thoughts about products? All right. Cool. I'll see you guys next week.
See ya.